All right, so let's start building some stuff here too. So let's make a geometry node here. Just call it example 1. All right, and let's just dive in there, and let's create a sphere. Let's do just a primitive. So just primitives are always just treated as a single point. It's going to be a bit easier to work with. Let's make it a little bit smaller. All right. So let's reiterate some of the stuff that we discussed in the PowerPoint. Let's make a wrangle. And if you don't know Vex, don't worry. We're gonna sort of be covering basics of Vex, and we're gonna do vops and Vex interchangeably, kind of during this course, and then hopefully it'll both make sense to you. But don't worry. For now, we're just gonna do some very basic stuff. So let's say we have this point here, and this point has a position. So position is 0, 0, 0, right? So we can say v at p. So the vector for the position. With p, you can also just type p, but v at p will tell it that it's actually a vector. Let's say we're gonna plus equals. We're gonna add something to it, and we're gonna add something between these sort of curly brackets. Or not, what do you call these weird things. We're gonna say 0. We're not gonna add anything to x. We're gonna add 1 to y, and we're gonna add 0 to z plus. All right, you can see position has changed. So position has changed very slightly. So if we were to change this to -1, it would go to 0, or to -1, to 2, etc. So let's maybe make it 0.1. So it's gonna go up 0.1. Not too interesting. But if we play through this, you can see nothing really happens, because this is not doing anything based on previous frame. If we want to do stuff based on the previous frame, what we need to do is, for example, we create a solver. So you've, like, probably most people who are probably watching this have actually played around with maybe with shelf tools and like with some presets and stuff like that. So there's multiple contexts in Houdini. You have a DOP network, which most of the simulation stuff actually happens in. So this is different context, and you have your pyro solver and your rigid body solver, stuff like that. So it's essentially a different context just for doing simulation, but you can also build stuff on SOP level with SOP tools. And you can build simulations there in a solver. So essentially solver is very simple. This is just gonna allow you to do stuff based on the previous frame. If you dive into it, you can see previous frame. So it's going to constantly look at previous frame. And this is what we're going to be essentially covering all throughout this sort of course. Because this is just going to be allowing us to create our own solvers, which is pretty dope. All right, so if we take this wrangle and paste it in here, and maybe call this manipulate position, something like that. If we go out of this, and now if we're now going to press play, you can see, whoa, it shoots up. Let's do that. Whoa, it shoots up. So this is because every frame is going to add 0.1. You can see, it's going to do that for every point. So if we were to plug a grid in here, see, the grid is moving up. So very simple example, but you can already see this is kind of what we're going to be doing, but like really in depth and making a lot of cool stuff. All right, so now let's do something with this example of what I was talking about in PowerPoint about just with random values. So let's put the grid in and scatter some of the points on there. So let's scatter a couple of points, and if we're gonna move upwards, you see you're just moving upwards like we expect. Let's make another wrangle. So let's just do our first our writing stuff here in SOPs, and then we're going to paste it in there later. Let's say we want these to move up at random speeds up. So right now they're just doing it to 0.1. Let's say we want to do it randomly for each point. So we could say, all right, so again, here's going to do some basic fact. All right, so we want to create a variable here. We're going to say float rand, and you could call this whatever you want. And we're going to say equals, and and this is going to hold some of our data. We're going to say, all right, we're going to want it to hold random function. So rand, and if you F1 over this is going to open up the help, and then you can see how it works. And if you're going to be coding, you do this quite a lot. You do float, rand, and then so it's going to say rand is going to generate a random number. You're going to generate it based on something. So you can see we can generate it based on a seed. You can add multiple seeds. So right now we're going to be using the point number. So we're going to say add pt_num. And you can see if we do this, nothing shows up here. So essentially, if you just type float and then whatever, or vector, or whatever you want to call it, this will just only use it within this, within this wrangle, and will not write it out. If we were to type f at rand equals rand, you see now it writes it out. So if I over here I would do f, so float at rand equals rand, you can see now it writes it out. But since we kind of don't really care about writing it out, because you only want to write it out if you need it later for something else, right? Because essentially this main point, and it's gonna just make it slower if you're gonna write out everything. So we would just want to keep it like that. Anyways, now we got a value between 0 and 1. We can check that. You can see just a whole bunch of random numbers between 0 and 1. You can fit these as well. Right, so now let's say v at p, or we can say at p.y. So you can get individual components, for example, of your vector. So x, y, and z. So that's another way of doing it. So let's say let's p.y plus equals. So we're going to add something to p.y. Probably be consistent and type v at p.y. So we know this is a vector. And we're going to plus equals it with rand. You can see now they're sort of randomly moving up. You can see some move up a lot, some move up very little. And let's put this one in between here. So instead of the other one that we had, and let's have a look at what that's going to do. You can see them essentially flying upwards. Some go very slow, some go really fast. And so we already made something that's sort of kind of cool. Another thing you could do, I mean, if we're doing some vex anyway, you can manipulate this, because this is always between 0 and 1. Maybe we don't want it to be between 0 and 1, so we could use another function here, and we can say rand equals fit 0, 1. So we're going to fit something that is between 0 and 1. And what is between 0 and 1? We can open this with F1. We're going to open something that is between 0 and 1, which is rand. And we're going to fit it between something else. So let's say 0.01 and 0.1. So now we're going to fit the value that was from 0 to 1. We're going to fit it between 0.01 and 0.1. So they're not going to move super fast, but they're also not going to be close to 0. See, if we're going to do that, you can see them sort of just moving upward. So you can see very, very quickly you can start to do some pretty interesting things just by iterating upon the previous frame. And one more thing that you could also do here, or discussing it anyway, we can also make sliders here for quickly be able to change stuff that's going on here. So we could say, all right, so you can make, let's make it a little bit easier to see. So let's float min equals, and then we're going to say channel float. I'm going to call it min. And by the way, you can use both these things as well as the this ones. But do whatever you like. So float max equals channel float max. All right. And then if you press this little thing, you can see we get a min slider and a max slider. We can just type our values in here, and then we're gonna, instead of typing it like this, we're gonna say min and max. Because I've also just created our sliders here, so you could have put this little wrangle over there. So that would just be channel float min like that. But you can see this might get a little bit, it's not as easy to read. So, but you can do whatever you like. But that way you you get some control over what you want to do. So if we go out here, now we have the stuff moving up, and let's say we want control outside of our solver here, because let's say we're going to make a pre-built solver, we could go edit parameter interface. We could go in here and we could grab our sliders here, drag them in, press apply. You see it links them up, and then we have controls over min and max right on our solver here. So you can imagine, like, if we're actually starting to build out some of our solvers ourselves, that we did stuff like this might be pretty good to do. Certainly you're actually starting to build tools. Anyway, let's do a slightly more interesting example. All right, so before we do anything more solver related, let's reiterate some stuff from Houdini 101. Just want to sort of take the point home about vectors and all kind of that stuff. So we're sort of on the same page in case you forgot all about those things. Because it's quite important to know at least sort of the basics on how like vectors work, what floats are, stuff like that. Let's just grab this sphere here and let's do an attribute vop. All right, let's dive in and let's make a noise. Turn on the noise. I'm gonna plug it in. There we go. And let's plug it into color as well. All right, there we go. All right, so you can see now we have a 1D noise and we're plugging that into color. And you can see we have R, G, and B. And you can see each value is going to be the same because we're plugging 1D noise. So one value into color is essentially going to map it into every single component. Yeah, so that's why it's just black and white. But we can, if we move, sort of move the offset, you can see it sort of animate along the thing. And we can increase the amplitude. We can change all of the stuff. So this is going to be a 1D noise. If you've ever seen a displacement map, usually they are black and white, and essentially that's what that is. So this is going to generally offset stuff in the normal direction, which we can try out. So that's how a displacement map would work. For example, is we could say, all right, what a displacement map would do is it would add the normal. So if we look, so this is normal. It's also a vector, so it's pointing over there. If we add normal to position, you can see it inflates. I guess the normal visualization isn't the exact vector. If we want to do a proper visualization for that, you can press D in the viewport, marker, want to visualize a vector, I want to visualize N. All right, there we go. And before we plug it in, you can see we have normal here. And then if we plug it into P, you can see, boom. Even though, right, it's of course the normals are gonna jump around, but you can see it's sort of, it's gonna offset the surface to the point where the normals are over there. And as you can see, that's exactly what's gonna happen. And then what the displacement would do is would take your texture and it's gonna essentially multiply the normal by your noise. Let's turn off our visualizer. And you can see essentially we have now offset our position by our noise here. You can see essentially it's how a displacement map works. So we're gonna offset our surface into our normal direction. So we can also do 3D noises, which is going to be a little bit different. So let's do a different VOP maybe, and we can keep this in the file. Right. We're going to have this noise here, and it also has an option for 3D noise. Let's make it 3D. Put it into color again. Right, there we go. You see, this gives us a color. So vectors can be visualized in different ways. You can visualize them as directions, or a vector can be a color, because essentially it's just 3 values. If you plug them into RGB, you're going to have a color. If you plug them into a position, it's going to end up in a position. If you're going to give it a direction, or it's like give it a velocity, for example, essentially, so it's going to be that. So visualize that in many different ways. Let's change our visualizer here, and let's visualize color instead. So type CD, let's turn it on. All right, so you can see now our noise here is both a color and just a essentially a representation of the vector on where it's pointing. So if we just move things around, you can see where this stuff is moving around. You can see it's sort of biasing in a certain directions because alligator noise between 0 and 1. If we take any of the other noise types, you can see it's going to be a little bit different. But you can kind of see what's going on there. And you can see with this stuff, you also have some stuff pointing in. And similar to what we do with the normal, if we were to add this to the position, because it's just a vector, and again, you can use vectors to manipulate stuff. If we add this to the position, you would see that stuff over here will end up over there, stuff over there will end up over there. And we can confirm this by plugging it in. Boom, and it actually happened, just like we described it would. You can see, let's see if we can, let's put a switch, so it's going to be easier to sort of to switch between these inputs. You can see stuff should end up over there. We can confirm it if we just put it right away here on the bottom, and you can see right exactly where we want it to be. So you can use these vectors to do different things. And again, this is what we're going to be using in our solver as well. Before we did that, I kind of wanted to reiterate sort of the point of this stuff, because this is going to be really important when we start building forces to advect points and stuff like that. All right, so let's start doing some of this, but then in our solver. Let's move this up. For this one, just call this move up, because that's kind of what this one was doing. All right, it was moving up. So let's grab our sphere here and let's scatter a bunch of points on it. And we're gonna want to do this on our points. Let's build another attribute VOP here, just so we kind of repeat the process and when we don't forget how it all works. So let's go in there and let's make a turbulent noise. And we want to add that to our position. 3D. Maybe do Berlin noise, because we don't want to be between 0 and 1. I want to add it here and then add it to the position. And now you might ask, Tim, why didn't you plug in position here? So in this case, we kind of want the noise to always be generated from the 0, 0, 0 position. Else, because we're going to make some points that are going to be moving around inside the subsolver. And if we're going to be plugging in the position of the points are going to change, and then sort of the position where the noise is mapped is also going to change every frame, and that's going to look a little bit weird. And I can give you an example of this. So let's actually just try this. Let's promote all of these parameters. And we're going to just put it in a solver, and you can kind of see what this is going to do. Let's make a solver. Let's actually plug it in here. Let's increase frequency. Let's do 0.1. And right now, if we're gonna play this, this is just gonna. All right, let's go out and let's actually highlight this. This is gonna move just as one sort of thing into one direction here, because we haven't really sort of told our points that they should sort of move freely, have their own free offset for each point. Like, let's say if we actually plug in the position for this, you can see that this is actually going to do something. And I probably want to change our type here, maybe original Perlin. All right, so you can see now it's actually is doing some stuff. Maybe you want to decrease the roughness and decrease the amplitude a little bit. So you can see they are sort of moving, and this actually does look kind of cool. You can see there, because they are sort of moving around and the noise is being applied for each point. This could be a cool effect that you want to do. I want to not do the position here, but again, then everything here is just gonna, let's reset. It's just gonna, well, right now it's not really doing anything. So we kind of want to do is we're gonna offset and we want to make a random value for each point number. So there we go, point number. And let's do output 3D vector. let's maybe fit range this a little bit. So we're gonna generate a random value based on the point number, and then we're gonna destination. Let's make it really high. Just offset our noise by that offset value. And now let's play and see what's gonna happen. Ooh, very fancy. Right, that's... Oh, by the way, this might actually be... So if you... All right, so if you haven't done it yet, if you don't have a... Because this might be where we want sort of the split interface. So let's do a just a default technical desktop. So if you want to... or let me just close some of mine. So let's say I want... Let's do close pane, close pane. So if you want to add sort of the split view, you can just go to these panels and then say split left, right. Split left, right. And you can link them here. So you can link these to two. So these are gonna behave as sort of the same window. So if I select this one, this is not gonna interfere with the other one. And you can link our view to one of the views. And this might be useful because maybe we want to work in here in our swap solver. But if we play in here, and this now as of 19.5, this actually does work. Before it would not update if you were in your swap solver, but just as a general rule of thumb, maybe you want to view outside of our solver, because I'm not sure, maybe it might still give some issues here and there. But link it to your second view, and now we can sort of play. You can see this stuff just moving around. Very cute. All right, let's make that noise a little bit smaller. Let's increase the... But you see this now essentially just sort of more exploding outwards. Maybe we want to also do some more interesting stuff. Maybe we want to sort of animate our value here of our offset based on our time, which might be interesting. So we could just do is we want to add something to our random value variable here. Or maybe let's do it after this thing. Let's add something to this value. Let's add our time. So that will mean our time will essentially manipulate the offset of our noise. If we look at what this is going to do, you can see now we're going to sort of get stuff that's sort of moving around like flies or something like that. So we can make a value in between here. And we can say, all right, let's multiply this, and we can give this a name called speed. So essentially what we're doing here is we're offsetting the position of where the noise is applied. So by default, it's applied to 0, 0, 0, and not to the position of each point. Then we're offsetting that position of the position of the noise. We're offsetting it by a random value based on each individual point. And again, like each point has a number. There you go. And then we're adding the time to that. So essentially the noise is also just moving through time. If we want to sort of, if you don't understand it, we want to visualize it here, we could plug our time into our offset in this thing here. And you can kind of see what that is doing. So essentially it's just animating our noise in all three components. You could do this individually for each component, of course, but for now, let's just do it like this. And then if we put a speed in between, promote it, and then we have a control over how fast do we want that stuff to happen. There you see. That's a little bit faster. Let's decrease the amplitude. We don't want this to be as extreme, maybe 0.05. All right, there we go. Maybe a little bit more, 0.15. You can see we're gonna get sort of cool stuff that's sort of flocking about, being all cool. Maybe make the amplitude or make the frequency a little bit smaller. You can see stuff is moving around. Pretty cool. All right, now let's say we want to copy some stuff to this to make it a little bit more interesting. So let's maybe do copy the points. Just dive in here, copy the points. Let's make a pig because pigs can fly. Here we go. And let's back an instance, and maybe let's make our little pig a little bit smaller. And if we're gonna play here, well, you can see they are moving around. They're just not oriented in the way that we want them to. So if we want to do that, we need to, of course, give them sort of a direction to look at. And we need to do that sort of in the solver here as well. So we could possibly do this by just having this noise that we have. Let's normalize it. So it's going to be normalized between 0 and 1. And now let's plug it into normal. And let's have a look at what's going to happen. Right, and you can see now, whoa, they're moving. They're doing, maybe let me decrease the points a little bit because it's getting a little bit chaotic. So you can see they're flipping over. That's just essentially what happens with normal rotations. Right, so if you didn't know, you might not know. We've briefly covered this in Houdini 101 as well. There's multiple ways to sort of do rotations. So there's Euler rotations and there's quaternion rotations. Essentially, with Euler rotations, what we're doing now is if we... I'm trying to think if I can do a good example of this. So Euler rotations is just what you have here. So you just have a all right. All right. So just rotate around a certain axis. But here you have something called a gimbal lock. So you have the wiki of gimbal lock. Just press this thing, right? So gimbal lock is essentially when sort of, if you have these rotational axes, if they end up in the same plane, that can cause issues. If you want to read more in-depth stuff, here is a whole article about it. But essentially, to solve that, you can make a quaternion. So quaternions are pretty much black magic. They're a little bit difficult to understand, but you don't necessarily need to completely understand them in order to use them. So essentially, it's a vector 4, and kind of how I understand it, and my description may be wrong. Again, you can Google it and read it for yourself. But here we have these normals. They're sort of moving around, and essentially sometimes if you're gonna copy something to this doing Euler rotations, you might experience a gimbal lock, and that's kind of when they're gonna sort of don't know where they're oriented and they're gonna flip once they sort of hit a certain threshold. Well, what we want to do is we want to make a quaternion. Essentially, we're going to give these points a direction that they know is up, and then they're going to rotate around that up vector. If we can visualize this again, I'm not sure if this explanation is actually correct because I'm not a mathematician and I just know how to use them, but I'm going to try to do this anyway, even though it might not be an actual accurate representation of quaternions, but this is how I see it and tends to sort of make sense to me. So, right, so let's say we have, all right, so we have an up vector. This line is going to be the up vector, and then we're going to have the x, the y, and the z, which is the vector component essentially. And because they sort of always have a direction they know is up, and then from there they're going to have a direction sort of where they're going to be pointing. And those 4 components make up the quaternion. And we can make this quaternion ourselves by just doing a wrangle, and we're going to say, all right, vector up. I'm going to make an up vector. Let's say just y is up in this case. I mean, and again, the direction that is up is going to depend, or we need to type in equals. It's going to depend how your pigs are going to be oriented. Right, so now in order to make a quaternion from our up vector and our normal, we actually first need to make a transformation matrix. And we need to make a matrix tree. So there's different types of matrices, essentially. You have a 3x3 and 4x4. Essentially 3x3 would be something like this. And then 4x4 would be an extra column over here on the right, and then with the extra column on the bottom there. So we need to make one, and then we can convert that into a quaternion. I know this might be a little bit tricky, but again, you just need to know how to do it, and once you know how to do it, you can just use it. And again, this is something you're going to be doing quite a lot. especially if you're going to be dealing with something like rigid bodies, where we're not going to be doing with this course, but that's stuff that's used a lot with rigid bodies. Anyway, first let's make a matrix tree. So, and we're going to say right equals. So we're going to make one. We're going to say make transform. And again, just open up the help file. Constantly always up the help file. All right, what do we need? We need a z-axis and a y-axis. All right. Well, we have a z-axis and we have a y-axis, which is up, which we conveniently made in the y-axis. All right, why are you complaining? Oh, we didn't give it a name. All right, let's call it just M3. All right, there we go. If we want to try this out and see it, we can say tree at M3 is equals M3. You can see this would write it out. This is a 3 by 3 matrix. You can see here's all of our data. As you see, it has all of our 9 components. You can count them if you want, but that's essentially what it is. All right, so now we have that thing. We can actually make it into a quaternion. So let's type at orient. So orient is a thing that Houdini recognizes orient by itself as a quaternion. That's essentially what you use for orientations. Again, we also covered this briefly in Houdini 101. So in order to make a quaternion from this, we just simply need to say quaternion from M3. All right, there we go. And now we have a quaternion. And if we highlight our piggies now, we should have piggies that are no longer flipping. They're flipping a little bit, are they? So like sometimes they do make sharp corners, but if you compare it to without it, so you can see stuff is really going crazy. There we go, and then with our quaternion, it's a lot smoother. It's probably if let's reduce the roughness here. Let's reduce the time maybe, and just want to show that it's sort of working. All right, there you go. Like sometimes they will, of course, go another direction and then they're gonna, of course, flip, but essentially they're quite stable. And if you turn that off, you can see them going to do weird things here and there. You see one flipping over. Well, if you do this, they will sort of just stick nicely into their direction. They're not gonna do weird rotations anymore. Let's see if I can pick one out that's doing something very specific. All right, yeah, here you saw one doing a loop-de-loop. If we turn it on, see it's just following its path. So yeah, and now we could make this, I mean, a little bit more interesting, even if you were to do, let's say we do trill. Yeah, because let's make these sperm piggies. Or before we do that, we don't need an ID in this case. Let's just do a trill. Let's trill some of these points. Oh, we do need an ID. So because if we're gonna trill this, we can see we get a trill, and we want to add sort of a line to this. And in order to be able to do that, we need to determine, right, which points do we need to add together. In this case, it doesn't matter if we do it before the sim or after the sim, because we're not changing point counts. So let's do another attribute wrangle. You can just do it after the sim here before we do the trill. Let's say just I at ID equals at ptnum. All right, so just have an ID, and let's do an add sub afterwards here. We want to add polygons, want to add them by group, by attribute, by ID. And you see we get some nice trills. And then maybe we want to sweep those. Want to do a round tube. Reverse cross section, apply scale along length. Let's see which we do it like that. All right. Let's merge this in with our little piggies. small, make the radius a little bit smaller. All right, and there we go. We got some sperm piggies flying around. Pretty cool. So you can see very quickly we sort of build our own little solver, just a very simple sort of particle solver, just points flying around. Something you would normally maybe do inside of pops, but now we've made our own little solver. And again, we're gonna be expanding upon this and really build a sort of a particle solver. It's gonna be able to do a little bit more, but you can hopefully you can already see sort of the cool stuff you can do if you sort of build your own little solver. So with this first sort of example out of the way, let's maybe have a look at some other cool stuff that we can use sort of this solver for, because like the possibilities are endless. Well, you can really make a lot of cool stuff in here. Just build your own solver with SOP nodes, which is like I love working in SOPs, and DOPs are always a little bit more confusing. In SOP solver, it's just essentially just using all of these SOP nodes to build your own logic. It's quite cool. You can do really cool stuff with it. So yeah, hopefully I'll see you in the next one.